So our last topic is something called a dot product of vectors. The learning targets here, we are going to do the first two. We are not going to have time to do the second day of this section. All right, so we'll just be looking at what is a dot product and how do we use it, and how do we find the angle between two given vectors. Okay. Vectors can be multiplied in two different ways, both of which are derived from their usefulness for solving problems in vector applications. So we have two types of products. The first one's called the cross product, or the vector product, or the outer product. Different books refer to it different ways. The cross product results in a vector that is perpendicular to the plane of the two original vectors. Okay, so you take two vectors in a plane, your dot product is actually going to be a vector perpendicular to that, which means we've now moved into three-dimensional space instead of two-dimensional space. All right, and that is beyond what we're going to do in this class. But vectors do come back. Not in the first year of calculus, but second and third year you'll hit some work with vectors. And you'll look at cross product. What we are going to focus on is called the dot product, or the scalar product, or the inner product. The dot product just gives us a scalar, just a plain real number. It's not a vector, just a real number. Okay? It can be positive, it can be negative, it can be zero. It's just a number. It is the important information conveyed by that number that makes the dot product so worthwhile. All right, a couple things just to refresh your memory. When we talk about vector u equaling that arrow PQ, remember we can pick that arrow up and move it anywhere in the coordinate plane. It's still the same vector, right? The notations. We've been using that first one. It's called Chevron notation, okay, where you have the first component, second component. Keep in mind that's equivalent to saying AI plus BJ. Okay, remember that I and j, I is a vector with length 1 in the horizontal direction. Okay, so it has components 1, 0, and j is a vector in the vertical direction, and it has components 0, 1. Okay, so we're just saying we're breaking this up into a vertical and a horizontal component. Okay. Vectors are used extensively in mathematics and science applications, such as determining the net effect of several forces acting on an object and computing the work done by a force acting on an object. Again, those are two applications that we aren't going to get to today. All right, but you will see them when you start learning about vectors in calculus. Or you can study them tonight if you want. Dot product. This is really difficult, so you need to pay close attention here. Okay? The dot product, or inner product, of two vectors is first component times first component plus second component times second component. I was kidding about it being hard.
You have no sarcasm.
You all are just staring at me like, I don't get it.
Well, you probably won't.
What's hard about that? Okay, I was being sarcastic. It is not difficult. Dot product. First times first, second times second, add them together. Okay?
Yeah.
It's probably the easiest thing you've done all year. Properties of the dot product. The first one says that the dot product is commutative. It doesn't matter if you do the dot product of u and v or v and u, you're going to get the same answer. Okay? Second one says if you take the dot product of a vector with itself, you get the square of the magnitude. Think about that. If you take the dot product of a vector with itself, you get the magnitude or length of that vector squared. Okay? Third one says if you do a dot product between the 0 vector and any other vector, you're going to get 0. Think about that for a minute. What are the components of the 0 vector? 0, 0. And if you take 0 times the first component, 0 times the second component, right? It just gets you a 0. The fourth one says that we can add vectors v and w together first and then do a dot product with u, or we could do the dot product of u and v, the dot product of u and w, and then add those together. Okay. Property 5 here says if we are taking a scalar c times u, okay, so we're stretching or compressing a vector, times, or with a dot product with a second vector. It really doesn't matter which one we multiplied by the scalar. Okay, we could multiply u by the scalar, we could multiply v by the scalar, or we could do the dot product first and then multiply that answer by the scalar. We're going to get the same result. Okay, we're actually going to prove the first two properties. So the first property says that the dot products are commutative. Okay, so let's look at u dot v. Okay, first times first plus second times second. So first component, u sub 1 times first component v sub 1 plus second component times second component, u sub 2 times v sub 2. But we know regular multiplication is commutative. So u sub 1 times v sub 1 is the same as v sub 1 times u sub 1. All right, same thing with the second part. We could rewrite that as v sub 2 times u sub 2. What? I wrote a 2 on the first one, sorry. There we go. Okay? But if you take first times first plus second times second, if you do that dot product, that's really the dot product of v with u, right? Because our v was our first components, u is the second vector. So it's really just saying that u dot v is equivalent to v dot u. Does not matter which order you put the vectors in. You're still taking first times first plus second times second. Okay? We are going to prove the second one, but let's go ahead and do a couple dot product computations first. So given two vectors, the first one has components 3, 4, the second one components 5, 2. We want to take the dot product. So first times first plus second times second. We get 15 plus 8, which is 23. I know that is so difficult. I expect you all to come in after school and get extra help. All right, second one. First times first plus second times second. What do we end up with? Negative 10. Okay? So again, dot product can be positive, it can be negative, it can be 0. The third example here, remember, is the same as if we had put it in component form, right? 2i minus j, you can think of that as 2 comma negative 1, right? Those are the first and second components of that. I would like you to be able to look at the ij notation and not have to rewrite it in component form. You're still taking first component times first component. You just don't have to worry about the i's and j's. Take them out. Okay? So 2 times 3 plus negative 1 times negative 5. Okay? So we've got 6 plus 5, or an 11 for a dot product. All right. Questions about the computation of dot product? Okay. We're going to go back up here and prove that second property. It leads into our next example. It says that we take the dot product of u with itself, we get the magnitude of u squared. Okay? So let's define u to be a, b. Instead of using all of our little subscripts, we'll just say we have two components, a and b. Okay? If we are going to do the dot product of u with itself, that means first times first would be a times a, and second times second is b times b. A times a is just a squared, b times b is b squared. Now remember, we're trying to prove that this is something to do with the magnitude of our vector, right? We're supposed to show that it's the square of the magnitude. How did we calculate magnitude? The square root of a squared plus b squared. So we've got part of it, right? We just don't have the square root symbol on top. So could we put a square root symbol in here, but then compensate by squaring it again? Right? Squaring, square rooting, cancel each other's out. And what we have in parentheses is the magnitude of our vector. So this is just saying we've got the magnitude of vector u, but it had to be squared. Okay? So that property gives us another way of figuring out the length of a vector. All right? If we already know the dot product, we can find the length pretty easily. So our second example says to go ahead and use that dot product to find the length of our vector u. We said u dot u equals the magnitude squared. So if we don't want the magnitude squared, we just want the magnitude, we'd have to square root the dot product. Yes? Okay, so let's figure out our dot product and square root it. Dot product is first times first. So we're doing it with itself, so 4 times 4 plus negative 3 times negative 3. Four times 4 is 16, negative 3 times negative 3 is 9. Added together we get 25. So square root magnitude here would be 5. Okay? All right, questions on dot product? All right, the second topic we were looking at is how do we find the angle between two vectors? It says let u and v be two vectors, two non-zero vectors in standard position as shown. So the tails match up. Okay, so we've got a vector u and a vector v. The angle between the two vectors is going to be something between 0 and 180, or 0 and pi. Okay. The angle between any two non-zero vectors is the corresponding angle between their respective standard position vectors. So again, if we have two vectors that aren't necessarily starting at the origin, remember we can pick them up and move them, right? They're still the same vector. So we can think of them in standard position. All right, this is a formula you're going to have to know. Highlight it, circle it, do something. It says if theta is the angle between the non-zero vectors u and v, then the cosine of theta is the dot product of the two vectors divided by the product of their magnitudes, their lengths. Okay? So to find theta, we'd have to do inverse cosine of that. Yes? Okay. We're going to skip the proof unless you really want me to go through it. You're okay with not knowing it? You just believe me that it's true? Okay. Example 3. Use an algebraic method to find the angle between the vectors u and v. Use a calculator to approximate exact answers when appropriate. So let's take a look at our first picture. We have vector u being components 2, 3. That means if we start at the origin, we've moved right 2 and up 3. Okay? Vector v has components negative 2, 5. So again, standard position, starts at the origin, we go 2 to the left and up 5. We are looking for this angle in between. Okay? The three things that we have to know for our formula. We need the dot product. That's the numerator part. And then we need the magnitudes of each of them. Okay? So let's calculate the dot product first. We have first times first plus second times second, which gives us what? We've got negative 4 plus 15, which is 11. Okay. Second thing, let's find the magnitude of the first vector here. So magnitude, remember, is the square root of the sum of the squares. So 2 squared plus 3 squared, which gives us the square root of 13. Okay. And then the magnitude of v, we need to take our first one squared plus our second one squared, add them together, square root it. We get the square root of 29. Okay, so we have all the pieces now. The formula said the cosine of theta is the dot product divided by their two magnitudes. So to find theta, we have to do inverse cosine of our dot product divided by the two magnitudes. Okay, now keep in mind, if you take the square root of 13 times the square root of 29, that's really saying we could figure out what 13 times 29 is, right? And then square root that. So on your calculators, you can enter this inverse cosine of 11 divided by the square root of 13 times 29, like that. You just want to make sure that that square root piece of 13 and 29 is all in the denominator. So if you want to put it in as two separate square roots, you can, but then put parentheses around the whole denominator. Okay? Go ahead and try it on your calculator. You should be getting about 55 degrees. If you're not, check that you have it in degree mode. And keep in mind that when we clear calculators before finals and other major tests, it goes back to radian mode, right? That's the default on your calculator. So always check that you've put it back into degrees. All right. Is that reasonable based on our picture? 55-degree angle seems reasonable? Okay. I'm going to pause the video. I want you guys to try the second one and then check with the people at your table. All right, let's check our second example here. We need the dot product. We need the length of each one. So dot product would be first times first plus second times second. So we end up with what? -5. Okay. Magnitude. We have first squared plus second squared, which gives us the square root of 5. And then for v, first one squared plus second one squared gives us the square root of 10. Okay, so to find the angle between the two vectors, we're going to do inverse cosine of what? Okay, dot product over the two lengths combined, the product of those. So again, you can put that in as the square root of 50. What do we end up with? Okay, now again, is that reasonable based on our picture? Okay, we went from quadrant 1 down here to quadrant 3. So we know we have to get something bigger than 90, right? Because we went past one full quadrant. Okay, so 135 seems reasonable. Okay. It says if vectors u and v are perpendicular, that is if the angle between them is 90 degrees. We said the cosine of theta is the dot product divided by the magnitudes, right? So could we multiply these magnitudes over here? Okay, that's what they're getting here. The dot product of u times v would be the two magnitudes times the cosine of the angle in between. Okay, it's another version of it. They're saying, what if the angle's 90 degrees? What's the cosine of 90? It's 0. So you take the two magnitudes and then multiply them by 0, you get 0. So if you end up with a dot product equaling 0, then you know that the angle between those two vectors was 90 degrees. Okay, that's a useful thing. All right, the last little bit that we're going to talk about. If two vectors form a 90-degree angle, you would say they are what? Perpendicular, that's the term that we're used to using, right? The term you're going to be using now is called orthogonal. It's very similar to perpendicular with one exception. So the definition here, the vectors u and v are orthogonal if and only if the dot product is 0. Okay? The terms perpendicular and orthogonal are almost the same. The one exception is when we deal with a 0 vector. It says the 0 vector has no direction angle. So technically speaking, the 0 vector is not perpendicular to any vector. Okay? However, the 0 vector is orthogonal to every vector. That was actually the third property of vectors that we looked at at the beginning of class today. You take a 0 vector and do a dot product with any other vector, you're going to get 0. Because what are the components of a 0 vector? 0, 0. So when you do first component times first component, second component times second component, they're all zeros. Okay? So the 0 vector is orthogonal to every vector, but it's not perpendicular to any. That's why we're using the term orthogonal versus perpendicular. But for every other case, they're the same. So when you see orthogonal, think perpendicular. We're not going to make that big distinction. Now I did add a little note in here about parallel vectors, because some of your questions for homework are these two vectors parallel, perpendicular, or neither. Okay? When we write a vector, remember we said we could pick that up and move it anywhere in the coordinate plane, right? And if we pick it up and move it, it has the same length, it has the same slope, right? Looks the same. So I can make a whole bunch of vectors that are parallel just by picking that one up and moving it. I can stretch it, make it longer, it still has the same slope. So two vectors are going to be parallel if one is just a scalar multiple of the other. Okay? So if I want vectors u and v to be parallel, what would my missing component be? It would be 10, because 2 times 2, if I double vector u, I should get vector v, right? So 2 times 2 gives me 4, 5 times 2 would give me 10. Okay? The other thing to think about is this is your horizontal component and this is your vertical component. So if you think in terms of the slope of that vector, it's just the vertical divided by the horizontal, right? Rise over run. So this u slope would be 5 over 2. Vectors v slope would be 10 over 4, but that's equivalent, right? Reduces to 5 over 2. So it's just another way of showing they're parallel. Okay? They have the same slope. All right. Proving vectors are orthogonal. To prove they are orthogonal, you have to show the dot product is 0. All right, so let's do dot product. We've got first times first plus second times second. We get negative 12 plus 12, which is 0. Okay. The last question for today, we have a picture on the left-hand side there. It is a half circle, semicircle. So segment AC would be considered what? The diameter. Yep. Okay, so AC is the diameter of that half circle. We have a point B up here with just generic quadrant components of x, y. And we have listed point A as negative A0 and point C as A0. I want you to notice right here. What is that? X squared plus y squared equals A squared. What does that look like? That's the equation for a circle, right? We think of it as x squared plus y squared equals r squared. Okay, so what they're really saying is for this particular picture, the radius is A, right? Does that make sense? From the center here, we're going A units to the right and A units to the left. Okay. It says figure 6.18 shows angle ABC inscribed in the upper half of the circle, x squared plus y squared equals A squared. We are going to go through a proof twice. The first time we're going to be given a specific number to use. The second time we're going to go through it with a generic variable. All right, so for the first one here, it says for A equaling 2, find the component form of vector U, which is represented by the arrow BA, and vector V, which is represented by the arrow BC. Okay, so we have vector U going from point B to point A. Yes? How do we find the component form of that? Okay, so we're going to take A minus B, the coordinates of those. Okay, so vector U would have components A minus B, so negative A minus X, and 0 minus Y. All right. Vector V. This one is going from point B to point C. So we need to take the coordinates of point C minus the coordinates of point B, right? End minus beginning, terminal minus initial, head minus tail, however you want to think of it. So A minus X would be our first component, and 0 minus Y would be our second. Okay, so we did the first step, we put them in component form. Step 2 says to find the dot product and explain what it means. So let's do the dot product of U and V. It says take first component times first component, which is a little more involved here. Sorry, we forgot to put 2's in, didn't we? They told us A was 2. Yes? I skipped right to doing it with the generic one. All right, let's go back. Let's plug 2's in for our A values. So this would be negative 2 here and positive 2. Yes? All right. So U dot V, we're going to take first component times first component. Okay, they're just more involved, not just a plain number. And then we have to add second component times second component. But what is 0 minus Y? It's just negative Y. So we've got negative Y times negative Y. All right. If we take the first component times the first component, we're going to have to FOIL that out. What do we end up with? Negative 2 times 2 would be negative 4. What about insides and outsides? Will they cancel each other out? Okay. And then last times last, negative x times negative x is positive x squared. And negative y times negative y is positive y squared. You good so far? Okay. But we were told right here that x squared plus y squared equals a squared. So this whole thing right here is just a squared. And a was 2. So that becomes 2 squared. So this is really negative 4 plus 2 squared. And 2 squared is 4. Negative 4 plus 4 is 0. So what does that tell me about my picture? If the dot product is 0, it means those vectors are orthogonal, which means the angle between them is 90 degrees. So from here we know that theta has to be 90 degrees. Okay, now we went through that proof, that algebraic proof, assuming A was 2. If we go back and put it back as just a generic A, does it still work? Okay, so vector U would have components negative A minus X, 0 minus Y, and vector V would have components A minus X and 0 minus Y. Okay. So let's go through and do the dot product again. We have first component times first component plus second component times second component. So if we FOIL this, negative A times A is negative A squared. Insides and outsides still cancel each other out. Okay. Negative X times negative X is positive X squared. Negative Y times negative Y is positive Y squared. But X squared plus Y squared equals A squared. So we end up with negative A squared plus A squared, which is 0. Okay? So we're really showing that anytime you have an inscribed angle like that, where the endpoints of those pieces are right on the edges of your diameter, it's going to be a 90-degree angle. Okay? All right. So you are going to do day 1, 1 through 24, 33, 35, and 36.